we're going to do potential for dividers now. I have drawn my circuit sideways like this, and I wish that all circuits were drawn like this, right from when you first start learning about circuits in year 8 or whatever it is. And the reason is because then we have a sensible idea about potential. And I'm going to talk to you about potential as opposed to potential difference. Okay, so potential difference is exactly what it says. It's the difference in potential, whereas potential is an absolute value. Right, now, before I go on to talk about potential dividers, I want to talk to you about wires. Now, when we do, I'm going to stop sharing this in there. When we do projectiles, or when we do moments and we're dealing with uniform beams, we talk about the fact that the beam is uniform. When we're dealing with projectiles, we talk about the fact that we're going to ignore air resistance. And we make explicit the thing that we're doing to make it possible for us to do the sums. You know, it's a light, inextensible string, and it's and we say we make sure it's clear, as clear as clear. For some reason, and I don't understand why, we don't do that with electric circuits, and yet there is an assumption there. Okay, when we're dealing with wires in electric circuits, those lines that join the important bits, the components, right? We tend to ignore the wires, and yet they then become a source of confusion. And what I want to do is I want to explain to you that when we're dealing with air resistance, or at least we say that, you know, ignore air resistance in this projectile question, and you can assume then that it's symmetrical and makes it possible to do the sums. In electric circuits, the wires, we assume that they are superconductors. Nobody ever says it, but that's what we do. We assume that they have not just a low resistance, but zero resistance. They're superconductors. If they're superconductors, then it takes no time for the charges to travel down the wires, no time. And it is not possible for there to be a potential difference along a wire if it has zero resistance. Now, of course, this is a simplification, but it's a simplification that makes it possible to do the sums in electric circuit questions. So, and I want to make it explicit that that is what we are doing when we deal with electric circuits. The wires have no resistance, not a low resistance, but no resistance, okay? And if we assume that, then there can be no potential difference across a conducting wire. If it's got a resistance, that's different. If it's a resistive wire, that's different. If it's kilometres long and we're dealing with a national grid, that's different. We deal with it as if it was a resistor then. But when we're talking about the connecting wires in electric circuits, we assume that they have no resistance. They are superconductors. Now, this is really important. If we do that, and we do all the time, we never really make it explicit, but we should. Okay, but if we do that, then what happens is that when we attach a power supply or battery or cells or something like I've got here, what the battery does is it maintains a potential difference across it, okay, and it will pump charge out to keep that happening, right? So what we've got in our circuit then is we can say that this end of my battery is 0 and this end of my battery is 12 volts, okay? But because everything attached to this 0, remembering that wires have 0 resistance, everything attached to the 0 end of the battery has to have the same potential. It cannot have any other potential because it's a conducting wire. So now this rail along the bottom we call the earth rail, or the 0 volts, okay? And we've got exactly the same, except it's all sitting at 12 volts along the top, and this is called the power rail. And when you look at electric circuit design, they quite often miss the power supply off the left-hand side. They just have a power rail at the top and an earth rail or the 0 volts at the bottom. And everything flows downhill. It literally flows from the top of the page to the bottom. That's the way the current, conventional current flows. It flows downhill. Okay. Right, now, the voltmeter that is across my my battery here has got 0 volts on one leg and 12 volts on the other leg. And voltmeters measure potential difference. Remember that the difference in potentials is the one minus the other. Okay, so 12 take away nothing is 12 volts. So guess what? That voltmeter reads 12 volts. Right, now, if I put in here a single resistor, I've attached it to the 12 volt rail at the top, so that's going to be sitting at 12. And I've attached it to the 0 volt rail at the bottom, so that's going to be sitting at 0. So if I put a voltmeter there, can you see that this leg is attached to the 12 volts? And remember, 0 resistance, it's got to be at the same potential. So that's going to be sitting at 12 volts. And this is going to be sitting at 0 volts. What is that voltmeter going to be reading?
Well,
12 volts, yeah, absolutely. It's 12 minus nothing, it's 12. Well done, well done, well done. Good. Okay, so now I'm going to remove it because adding in voltmeters, they don't take part in the circuit. They don't count as part of the circuit unless they've got a low resistance, in which case you can deal with them as if they were a resistor. Okay, right, now imagine now that I've got two identical resistors I've put in my circuit. Right, now the top of this one is attached to the 12 volts, so that's sitting at 12, and the bottom of this one is attached to the 0 volts, so that's sitting at 0. What I want to know is what is my potential at X. Now these two resistors are exactly the same. So if I've got two resistors exactly the same, then my potential is going to be divided equally. And I've got 12 volts, so I should have 6 volts across one and 6 volts across the other. So what's it going to be sitting in the middle? Yes, indeed, it's going to be sitting at 6. Can you see this is going to be at 6? And if I now put my voltmeter, let's make it red this time, across this resistor, I've got 12 volts on that leg and 6 volts on that leg. Remembering that voltmeters measure potential difference, it's going to be 12 minus 6, which is 6 volts. So that voltmeter will be reading 6 volts. And if I do exactly the same across my other resistor, can you see this is connected, so it will also be at 6. This is now connected to the 0, so that's going to be sitting at 0. My voltmeter will be reading 6 minus 0, which is, oh look, 6 volts. I've got 6 volts across each of my resistors. Okay, good. Right, let's get rid of all my red stuff because it's complicated and makes things difficult. Right, so now what I'm going to do is I'm going to do 3 identical resistors. Right, now remember that the potential is divided the same way that the resistors are divided. I've got 3 identical resistors. So my 12 volts is going to be divided into 3 equal parts. 12 divided by 3 is 4. So I want to know what is my potential at X. Good. It's going to be at 4. Okay, that's my potential at X. Right, what is my potential at Y? my potential isn't 4. Some of you have got it. My potential at Y is 8. The potential difference across the middle resistor is 4. But my potential at Y is 8. Can you see what's going on here? If I go back to red for my voltmeter, if I put my voltmeter across there, it's going to read 12 minus 8, which is 4 volts. If I put my voltmeter across there, it's going to read 8 minus 4, which is 4 volts. And if I put my voltmeter across there, it's going to read 4 minus 0, which is, oh look, it's 4 volts. Now can you see the difference between potential, which is the little black numbers, and potential difference, which is my readings on my voltmeter? Right, now, I am now going to ask you to do something that very rarely comes up in questions, but it's really revealing when it does. Okay, what happens if I put my voltmeter there? What will it read?
Isn't it 0 because it's wire?
No, the voltmeter does not count as a wire. In fact, an ideal voltmeter has infinite resistance. So no, it's not a wire. No, 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 it's not a wire. Yes, Muboni, it is. Can you see that this end is sitting at 6 volts and this end is sitting at 8? Because this end is connected to the 6 volts and this end is connected to the 8. So what we've got there is a difference, potential difference, because that's what voltmeters measure, 8 minus 6, which is 2 volts. Can you see why it's 2 volts? Okay. Can whoever put the selected the things in blue, yeah, thank you. Right, I'm just getting rid of my my voltmeter again. Right, now what I'd like to do now is I would like to do 4 identical resistors in series. That is still connected to the 0. That is still connected to the 12. These are all identical. So they are going to divide my 12 volts equally into 4 parts. What's 12 divided by 4? 3. Okay, so across each of these resistors is going to be 3 volts. So from 0 to here, that one there is going to be sitting at 3. What's this middle point? I'm going to put an X there again. What is the potential at X? I'm not talking about potential difference, I'm talking about potential at X. Good. 6. Perfect. Okay. Okay, I'm moving my X. What is potential at the new X? 9, yes. Okay, you're beginning to get it, aren't you? Okay, right, now I'm going to do something weird. If I take a wire, my green wire, and I attach it like that. If they're not, I'll come to that. I promise I'll come to that, Gareth, okay? I promise, right? If I connect a wire, a green wire, like that, on the top, right, can you see that everywhere on that wire is still sitting at 12 volts? Because it's a wire and it's a superconductor, remember? And because the wire, the black one that goes straight along the top, has no resistance, not just a small resistance, no resistance, adding the wire in parallel, doesn't reduce my overall resistance. So will that green wire that I have put in there do anything? Will it change anything? No, it won't. It will do nothing. It will do nothing. Right, now, weirdly, I'm going to get rid of my green wire. Weirdly, if I now, I know it's an old thing to do, connect my green wire, not to this one, I'm hopping over that one, it's not attached there, it's attached there. Will that green wire affect my circuit in any way? Taha, what is a short circuit? What's the definition of a short circuit? Okay, so a short circuit, different smaller path for the current to take. Right, so a short circuit technically is connecting one end of your power supply directly to the other with a wire and bypassing, shorting out all of the components in your circuit. So, and what happens is that the current goes through the wire, that goes directly from the positive to the negative, and none of the rest of your circuit gets powered at all. If you short out a component, you put a wire in parallel with it and the current goes through the wire instead of through your component, and it's like your component isn't there. Okay, so it's called shorting out. So no, this does not short out anything. Why not? Can anybody see what that will do, that green wire? Or will it do anything?
You're going to take the potential difference between the three branches, isn't it?
Well, yeah, except that there isn't a potential difference, right? It's not connected to the middle one. It's only
Oh, is
connected.
it not? So yeah, it's zero then.
Yeah, so there's a potential difference across that wire of nothing. So that wire is not going to do anything. There won't be a current flowing through it. There's no potential difference across it. Nothing. That wire will do nothing. 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 Which is weird, right? Okay. Right, let's try with what Gaurav said. Okay, so now I'm going to do two resistors, but one of them is completely different to the other. Okay, right, now, is that only because there was potential of 6 volts on either end of the wire? Yes, exactly that, Anika. Exactly that. Yes, if there was a potential difference between one end of the wire and the other, remembering that you cannot have a potential difference across a wire, it's a superconductor, it would change the whole circuit. It would turn the resistance, it would be very different, it would have a big effect. But because the two ends are at the same potential difference, it makes no difference to the circuit. I know, it's weird, isn't it? Okay, it's called a null, oh, I can't remember, null something or other. Anyway, it's because the same potential on both ends, nothing happens. Right. Okay, now these two resistors, so if they are not the same potential, they're right. If they're not the same potential, then you change the circuit and then that's different. Okay, so it's only if the two ends are at the same potential. Okay, right now, I am going to say that this resistor here is 5 ohms, and this resistor here is 10 ohms, right? Now, the bottom one is still connected to the 0. The top one is still connected to the 12. Now, what I want to know is what is the potential at X again? Right, now, this is the potential divider equation. It says R1 over R total is the same fraction, it's a divider, as V1 over V total. Okay, that is the potential divider equation. Basically, the potentials are divided the same way that the resistances are divided. Okay, now what is 10 as a fraction of 15? Yeah, absolutely, it's 2/3. Okay, and that is going to be my potential difference across my 10 ohm resistor. That's V1 divided by 12, because that's my total potential. So basically, my potential difference across my 10 ohm resistor is going to be 2/3 of 12. What is 2/3 of 12? Yeah, 8. So X is going to sit at 8 volts. Can you see how we've worked that out? Oh, sorry, I've got a puppy howling. Oh, hang on. Come on. Yes. Sorry, she's been left on her own, I think. Oh, it's so sad, isn't it? Isn't it? Her name is Boo. Yeah. Anyway, right, okay. So now we are going to do a few more like this. You make it, everybody makes it so complicated. All it is just the same fraction for the voltage as it is for the resistances. That's all it is. Right, so we're going to have a resistor and a motor this time. Okay, the motor has a resistance, let's make it, I don't know, 20 ohms, and the resistor is going to have a resistance of, let's make it 6 ohms, so that it's not nice numbers now. What is, right, this is still 0, this is still 12. What's the potential there? I'll get rid of this X. Stick with X's all the way through. So what's the potential at X? What's the sum we've got to do? Can you see? We've got to do 20 out of 26 is equal to V over 12. Yeah. So it's 20 out of 26 times 12, which is, or somebody's done it, 9.2, I believe you. 9.2 volts. It sounds about right to me. Okay? Dead easy, right? So now my voltmeter between there and there is going to read what? What's my red voltmeter going to read? 1.2 volts. Yes, it's the potential difference. Yes! Cooking with gas. Cooking with gas. Right. Now, several more things to say before we go on and do some sums with this. Okay. Right. The current from the power supply goes up every time you add in an extra branch. But have any... Oh, thank you very much for that little comment. Gaurav has said, thank you so much. This is genuinely a topic that haunts me. Yeah, there you go. Okay, right now, what I was going to say is, right, every time you add a branch, more energy is drawn from the power supply. So the current through the power supply goes up. And in fact, the currents down the power rails, they go up as well every time you add in an extra branch. But have any of the resistances and any of the potential differences in the vertical columns, those parallel circuit segments, have any of those resistances or potentials changed because I've added in an extra vertical column? No, they haven't. And actually, this is how your house is wired. I mean, I know it's AC, not DC, but basically everything in your house is wired in parallel. And you wouldn't expect when your washing machine comes on for your lights in your bedroom to dim, would you? They don't do that. And you wouldn't expect when you turn your electric oven on that your TV would go like that. You wouldn't expect it. It doesn't happen. And that's because the full 235 volts or whatever it is across your is across every single component that you plug into the mains. Every single one gets the full potential difference because everything in your house is connected in parallel. Even in cars, every headlight, every windscreen wiper, every window winder, every mirror adjustment motor, everything is connected in parallel. And so none of them affect each other. And can you see that the currents flow downhill? And the potentials, they are just exactly like height. So when we talk about gravitational potential, which you also will find difficult because it's a very abstract concept, those go up with height. Well, can you see if you set out your circuit this way, the electrical potentials go up with height and current flows downhill. Oh, just like, rivers, they flow downhill, don't they? Current flows downhill. Oh, okay. Now, can you see how useful this is? Right, now, several more things to say, right? First of all, the next thing to say is that you can do V equals IR and P is VI and all those 3-letter electrical equations. You can do them on any aspect of your circuit. So you could apply V equals IR to that resistor, or to that pair of resistors, or to that pair of parallel circuits, or you could apply it to the battery, or you could apply it to the whole thing, right? But when you do, say, V equals IR on your whole circuit, you have to use V for the whole circuit, which in this case would be 12, I for the whole circuit, in which in this case it would be the current through the battery, and R for the whole circuit. So you'd have to work out what the total resistance is for all of those things in parallel. Now, can you see that you've got to have, and this is the way I express it, you've got to have sets of things that go together. So you can apply V equals IR or P is VI or anything, okay? You can do that to any part of your circuit, but you have to have a set of things to go together. So it might be V total, I total, R total. You have to have sets that go together. Right, now when it says 9.2 volts on the wire from the calculation using 20 ohms, how do you know which resistor to use for the potential in that wire? It's the one that's attached to the 0. Because you could do the 6. Let's do the 6, okay? So Annika, let's do the 6 ohm. So it's 6 out of 26, isn't it? Times 12. That is going to give us the potential difference across the 6 volt. So what we're going to get, let's do it. What do we get? We get 6 divided by 26 times the 12 gives us 2.8. Okay, so this is 2.8 volts. Right, now what that says is, let me change to let's go purple. That means that there's 2.8 volts across there. Now that top one is at 12. So you do 12, take away 2.8. Can you see? The difference is 2.8. 12 take away, well, it's actually 9.2, isn't it? 12, take away the 9.2 is 2.8. So that gives you the potential difference across that 6 ohm resistor. So now we can work out what the potential is between the 20 ohm motor and the 6 ohm resistor, and it's 9.2 volts. Ah, now she's beginning to get it. This is potential difference, right? It's like the change in height, right? Is the positive battery terminal always the power rail? It's much easier if it is. I mean, technically, you could attach the positive battery terminal to 0 and then all of the potentials would be negative. Could do that. Why would you do that? That just makes it difficult to think about. But yeah, you could do that. You could attach the bottom end of your power rail to 4 volts if you wanted to. And then the top end would be 12 plus 4, which would be 16. Oh, okay. And then the potential difference, but can you see that's not helpful? So most people don't tend to do that. So we don't go the way of conventional current. Yes, we do. Conventional current goes from positive to negative. So it goes up, across and down. And back to the 0. Goes from positive to negative. The arrows on that diagram show the way conventional current flows. Oh, no. I mean, yeah, batteries pump. They pump the charges. They separate charge. That's what they do. So it's kind of like pumping the charges back to the top of the hill. It's an electrical hill. Okay, right. Okay. Right, so hopefully this has helped you a bit. I mean, there are still other things that you have to remember from year 12. So Kirchhoff's laws. So the currents at any junction add up to nothing. So currents in equals currents out, if you prefer to say it like that. And that's a statement of conservation of charge. You need to remember that EMF is where power or energy is going into the circuit, so that's across your power supply or your battery or your cell or your generator or the mains if you're dealing with mains, or your power station if you're dealing with a power station. And potential difference is the voltage across where the energy is coming out. So that's what, right, all electric circuits do the same thing. They move energy from one place to another place, from one type to another type. Okay, so and that's all electric circuits do. If electric circuits don't move energy, they're useless. Okay, when you flick on a light switch, you're turning electrical energy that comes from the mains into light energy, well, and heat often. Okay, if you are switching on your washing machine, then you're turning electrical energy into kinetic energy and heat. Okay, if you are switching on your TV, then you're turning your electrical energy into, well, sound and light and probably some heat, which is by accident, that's wasted. Okay, but all electric circuits transfer energy from one place to another place, one type to another type. And the reason they're so useful is because you can literally do it at the flick of a switch. So amazingly useful electric circuits. Right, now I hope that you've kind of got the hang of this now. Let us apply this new knowledge to our questions. So I close that. I'm going to pull across some potential divider questions that I have previously prepared, and I'm going to share my screen. Let's make it a bit bigger, shall we? So you can see, right now, this is a classic potential divider. Right now, using our new ideas about potential as opposed to potential difference, we can say, well, we've got a 9-volt supply. It says there's negligible internal resistance. So there's no internal resistance. So basically, we've got 9 volts across there. So let's make the negative end 0 volts. So we're going to call that 0. So this is 0. So this is 0. So this is 0. And this end is 9. That's 9. That's 9. That's 9. That's 9. Okay. So now what we got to do, it says if the EMF of the battery is 9, which it is according to there, R1 is 120 ohms. That's 120 ohms. And R2 is 60 ohms. Right, the first thing they ask us to do is calculate the current flowing in the circuit. Right, I don't want to do that first because that will encourage you to use V equals IR. I want you to use the potential divider equation. Okay, so let's not do not part 1 anyway. Let's move straight on to calculate what that voltmeter is going to read. Okay, can you see, I hope you can, that the potential across there, V over V total, is going to be the same fraction as R2 over R total. R2 over R total. Right, now R2 is 60. Our total is 60 plus 120, which is 180. And that is equal to V, which is what we're trying to get, and V total is 9. Well, 6 out of 18 is a third. A third of 9 is 3. So this V is going to read 3 volts. Can you see why? You squeaking? What are you squeaking about? Okay. Right, I'm going to clear all my drawings. Let's now do it the way they want us to. Remember that this is 120 ohms and this one is 60 ohms. Right, it says calculate the current flowing in the circuit. Okay, which equation are we going to use to calculate the current? V equals IR. Right, now remember that we have to have a set that goes together. Well done, Annika. So we're going to go V total, I total, R total. Okay, we want I, so we're going to rearrange it. It's V total over R total. Our V total is 9. Our R total is 60 plus 120 because resistors in series add. So it's 9 over 180, which is 0.05 amps. Okay, yes, well done, well done, well done. Excellent. Okay, nice, isn't it? Lovely, perfect. Okay, this is not the hard bit. This is the hard bit. Right, it says, the circuit shown in the diagram acts as a potential divider. The circuit is now modified by replacing R1 with a temperature sensor whose resistance decreases as the temperature increases. What's the name of a device whose resistance decreases with temperature? Thermistor, yeah. Okay, so, and a thermistor has this symbol. That's a thermistor. Okay, and if we were to draw resistance with temperature, C or whatever, it was this, something like that. Okay, this is in ohms. Right, so that's a thermistor. Right, now we're replacing R1. R1 with the top one or the bottom one? I can't remember. The top one. Okay, so what I'm going to do is I'm just going to sketch our new circuit. Okay, remembering our Ninja question reading, we're going to draw the situation. In this case, there is our thermistor. R2 is the same, presumably it's still 60 ohms. Okay, and we've got our voltmeter across that one. This is still 9 volts, presumably. So this is 0, 0, 0, 0, 0, 0, 9, 9, 9, 9. Okay. All right, so let's go back and read the question again. It says, the circuit shown in the diagram acts as a potential divider. The circuit is now modified by replacing R1 with a temperature sensor whose resistance decreases as the temperature increases. Right, now, this is a classic explain. Explain whether the reading on the voltmeter increases or decreases as the temperature increases from a low value. Right, now, we haven't done the command words yet and how to scaffold them, but the explain command words, the hardest of the lot, and it has a very, very particular structure, the way you answer an explain question. And explain, then, the structure of your answer is key fact, consequence. Right, now, this is a 3-mark explain, which means that we've either got 2 key facts or 2 consequences, and we score 1 mark for each key fact and 1 mark for each consequence. Okay. What we've got to do is explain what happens to the voltmeter reading, this reading, when this changes. Why does this change? Can you see? What's our key fact here?
Resistance changes with temperature.
Perfect. Can you see that if you know that that is the structure of your explain, you've got no option about what is the key fact that causes anything to change in the circuit? And we're asked about whether the voltmeter reading increases or decreases. So we're asking about what's changing. So the thing that's changing is the temperature. And the temperature is going to cause the thermistor resistance to change. So that's our key fact. Can you see? Suddenly it's not vague or woolly. It's got to be that. That's our starting point. Okay, so our starting point, our key fact is the resistance of the thermistor. Right, it says we're told that it decreases as the temperature increases, decreases as the temperature increases. So what's the consequence of that? The resistance here, this resistance, goes down.
Would we say that the voltage is proportional to R, therefore the voltage would also decrease?
Right, you could put in a second key fact. What would be your second key fact? It's not the proportional thing.
V equals IR.
No, I wouldn't use that one. I mean, you could, right? You could do that. I mean, right. Okay, you could do that. Let's do V equals R, because that's obviously more comfortable for you. So if the resistance of the thermistor has gone down, what happens to the total current, the total resistance in the whole circuit?
Well, decreases.
Right. So we could have a second key fact. Okay, the total circuit resistance has also decreased. Right, I can't be bothered to write it out, but that's what you'd say. Okay, so if the total circuit resistance decreases, right, we've got another key fact, haven't we? We've got V is equal to IR. So, and that's total. So yes, you can, Gaurav, and that's what I would want to use. Okay, but can you see? I could say, well, what happens to I? What happens to I? If the total resistance goes down?
It doesn't just stay constant because the
Look at this, look at this. What happens to I if the total
increases.
resistance has gone down?
Increases.
Yeah, right. So if the resistance decreases, Taha, can you see it's on the bottom of the circuit of the equation that I've put in the box? So if resistance decreases, I increases. Okay, so I increases. So you could then say that consequence of that is that I total increases. So right now, can you see that we now have to apply V equals IR, but to the 60 ohm resistor, the 60 ohm resistor, the 60 ohm resistor? Well, it's a series circuit, so I60 is the same as I total, and I total has gone up. R60 hasn't changed because it's a 60 ohm resistor. Yeah, okay. So R60 is not changed because that's fixed resistor, but I total, that has increased. Okay, so what happens to V across the 60 ohm resistor? Can you see this is another key fact? So the consequence of that is that V60 goes up. Yeah. Now, can you see this has made a 3 mark explain into a 1, 2, 3, 4, 5 mark explain. So, which is one of the reasons why I don't like doing it with V equals IR. I'd much rather use the potential divider equation. That's what it's for. Makes it ever so much simpler. So let me clear all my drawings in there. Okay. Right now, again, we still have the resistance going down with increasing temperature for our thermistor. Right. Now, can you see that if I want to do the potential across the 60 ohm resistor, which is what they want us to tell them about, because that's where the voltmeter is in the circuit, I could say, right, if I call this R2 and this R1, right? Can you see that I can say that my key fact is still that as the temperature goes up, the resistance of the thermistor R1 goes down. Okay, so that's my key fact, right? And then my next key fact, I'm going to have a second key fact, is that R2 over R total is equal to V over V total. And this is 9 volts. Okay, so I can then say, can you see that that's my second key fact? I mean, I might want to put it in words, so I'd say that the resistances are divided the way, or sorry, the potential differences are divided the way the resistances are divided, and then write the potential divider equation. But then can you see the consequence of that is, right, R total is R2, it's 60 over 60 plus an R has gone down. Okay, so it's 60 divided by a smaller number, which means that V is going to go, because V total is 9 still, isn't it? Can you see V is going to go up? The number on the denominator has gone down, which means that, can you see it's still multiplied by 9? Let's put that in there. You see? The R has gone down, so V has to go up. So V, it's the voltage across the 60 ohm resistor, increases. Can you see that now I've got a 1, 2, 3 mark explain? And this explain what happens to the potential difference across a resistor in a potential divider circuit comes up every other year. So this explain, this one, is one of the ones that it's a good idea to go away and actually learn by heart how you're going to write your answer. So you need to say, I mean, it's not always a thermistor. Sometimes it's a light dependent resistor, and the resistance changes with the amount of light. Okay, but basically it's still your potential divider equation, and then a conclusion from your potential divider equation. Okay, hopefully this all makes sense. Okay, let's do another one. Clear all my drawings. That's that resistivity. Right, okay, I think we can deal with the second half. Right, it says, in the circuit shown, each resistor has the same resistance. Right, I'm just randomly going to say 10, 10, 10, 10, 10, 10 ohms. It doesn't matter. They've all got to be the same. I could just write R, but I've written 10. Okay, right, it then says, battery has an EMF of 12. So if there's 12 volts across there, and we say that this is 0, let me do it in a different color. Let's say that that's 0, 0, 0, 0, 12, 12, 12, 12, 12. Okay. Okay. We've got our 12 volts divided by 3, haven't we? 12 divided by 3 into 3 equal parts is what? 12 divided by 3 gives us 4. So this point here is going to be at 4. C is going to be at 4. What's A going to be at? 8. Good. 8. Right, now calculate the potential difference between A and B. A, right, let me go to a different color. Let's go green, A, and B. Can you see this is going to be 0, this is going to be 8. What's it going to be? 8 volts. Calculate the potential difference between B and C. Four volts. Well done. Can I reduce this line? Oh, I've got to get rid of all my drawings if I do that. Clear all my drawings. Right, it says a high resistance voltmeter, that's an ideal one, is connected between A and C. What is the reading on the voltmeter? Remember that this was 0, 0, 4, 4, 8, 8.
That also 4 then.
Yeah, it's going to be 4 volts, isn't it? Can you see how easy this is now? I hope you can. Wow. Okay, let's do another one. Right, now here, what we've got is a pointer that's sliding. So we're dividing the same resistance. So our total isn't changing here. What's changing is which fraction is above and which fraction is below our pointer, where we're sliding it up and down the resistance, okay? So imagine that this is 12 volts. When the pointer is at the top, can you see this is 12, this is 12, this is going to be reading 12, this is 12. And this is 0, this is 0, this is 0, that's going to be reading 0. So there's going to be 12 volts across that. That thing, by the way, is an old-fashioned diagram for a bulb. So think of it like that, okay? So you'd have 12 volts across your bulb, okay? And if what you did was you slid your slider to B, Now, can you see at B we've got 0, so this would be 0, this would be 0. Across our bulb we'd have 0, which means that it would be off. It wouldn't be glowing at all. Okay. Right, now in this second example, can you see there's no wire here? Which means that, well, what's going on, right? This is 0, 0, 0. This is going to be 12, 12, 12. But whatever that resistance is there, represented by that length, that is going to be in series with our bulb. Okay? Which means that if we slide our slider thing to the top, we've got 12 volts across our bulb, and our bulb will be a light. And if we slide our slider thing to the bottom of that, can you see we're going to have, well, whatever that resistance is compared to that one, that's going to divide that potential, that 12 volts, that way. Can you see? Okay, right now, all of the current in the second circuit, all of it goes through the bulb. All of it. It's a series circuit, this one. In the first circuit, the current is split there. Some of it goes through the bulb and some of it goes through the second half of the resistor. It joins again at that second green blob and goes back through the battery. Can you see that this is a parallel circuit? This is a series circuit. So all of the current goes through the bulb in the second circuit, which means it's less wasteful. But you don't get as big a variation control on the voltage. Okay? Can you see why that is? I hope you can. Okay, right, let's look at this one. We've got 2 or 3 minutes, that's all. Okay, so the figure below shows a simple light sensing circuit. When the output voltage V, this is the output voltage, okay? It's a potential difference across there, that potential difference. When it falls below 2 volts, right, let's make it 2 volts. This acts as a signal to switch on a safety lamp. So this is a sensing circuit. The LDR, light dependent resistor, has a resistance of 1.25 kilo ohms when it's in the light and 150 kilo ohms when it's in the dark. Okay, so we've got, this is dark, this is light, so this is light level, and this is resistance, and it goes, and it's in the dark it's really high, and in the light, so this is 1.25, and this is in kilo ohms, and here in the dark it's 105 kilo ohms. Okay, so from 100 down to 1-ish. Okay, so and it says the battery has an EMF of 6. Okay, so this is 6, 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 this is 0, this is 0, this is 0, this is 0, this is 0. Okay, it says show that the safety light will come on when that says 2. When that says 2, that's when it comes on. We were told that when that says 2. Look there, when it goes to 2. So if the resistor has the value of 50,000 ohms, so this is going to be 50. What's that going to be to give 2 volts? Can you see what we've got to do? Right, our potential divider equation then is 2 over 6, that's our V1 over V total, is equal to R over R total, which is 50 over 50 plus whatever the resistance is for the LDR. Okay. So hang on, right, if it's dark, the LDR resistance is 105. So I can replace this. Oops. I can replace this one with 105 kilo ohms. 105 times 10 to the 3. Right, now I could replace that with R. And then, can you see, this is 1/3. I've got R over R plus that thing is equal to 1/3, because 2 over 6 is 1/3. There, I can solve that for R, okay? Incidentally, there's a trick that you can do, okay? So I'm going to show you the trick. Let me get rid of all of this in a minute. Right, if instead of doing the 2 up here, we do this 4 volts, because it's 2 volts plus 4 volts gives us our 6 volts. So instead of doing the 2, we do 4. We do 4 over our total voltage. So that's VLDR over V total is equal to R over the LDR over R total. I don't write the whole word total. Right, can you see that then is 105 times 10 to the 3 over 105 times 10 to the 3 plus R. And now, if I do it that way round, I've only got R in there once. So can you see that equation is easier to rearrange than the previous one, because I've only got my R in there once. So the trick is to do the potential difference for the resistor where you know the resistance, and then work out what the other one is. Okay. I hope that this has helped you with your LDR, your potential divider questions.